Good morning, everyone. Thanks for the introduction, Colin. It's always a pleasure to be a presenter in this series of WoodSolution webinars. Okay. Without further ado, I would like to start the presentation and basically go through the slides I have provided for today and show what it means when you talk about development of a hybrid system, in this case, a reinforced timber frames. And apart from showing some laboratory test results, we go through some simplified design provisions, which we have developed over the past few years in relation to design of reinforced timber frames. All right. Okay. Now, let me start with, let's say, why we are reinforcing timber. All right. And then from there, explain what are the aspects of these reinforced timber frames and what's really important about it. Essentially, we reinforce timber to enhance the structural performance, and that basically paves the way for use of low-grade timber. And when I say low-grade timber, some might argue, there might be lower grades than what you're showing, but these are the range of low-grade timber we have utilized in our research project, and we have extensively done experiment on. So essentially, we are looking at application of Douglas fir as well as pines. The range is like F5, F7, and then GL8, which is glue laminated timber made of radiata pine, and then MGP10, of course, which is not exactly the lowest grade timber you can find in the machine graded pines, I would say. So when I talk about structural performance, I just want to make it clear, we are talking about strength or load carrying capacity, stiffness, and ductility. Three characteristics which are prime importance for structural engineers and design of structures and its performance during its design life. Now, in terms of type of reinforcement, a wide range of reinforcement have been explored over the past century, I would say, starting with the use of, let's say, steel plates that led to development of, let's say, flitch beam. They have been used for over a century. But in more recent years and recent decades, we have seen application of, let's say, fiber reinforced polymer as an alternative for reinforcing timber, especially started from early 90s. And then in more recent years, again, I've seen even aluminum used for reinforcing timber with some improvement in structural performance. Now, to reinforce timber, we could use bar rods or we could use plates and strips. Those plates and strips could be installed or applied externally or internally. And here are a few examples of external and internal, let's say, plate strips used for reinforcing timber. As you might know, the main challenge of using this external strips or plates is essentially fire. And when these external reinforcements are subjected to elevated temperature or fire, the strength and stiffness rapidly drops or degrade and deteriorates, and that would affect the performance. And hence, we are looking at other alternatives, specifically these two alternatives shown here, where the steel bars completely embedded or encased in timber. There are certain advantages in relation to use of encased steel bars. I have provided a list in this box. And apart from, of course, enhancement in structural performance, there are other advantages which are less, let's say, known. For example, preventing buckling of the steel bars is one alternative, or one of the advantages. Inherent fire protection provided by timber for the steel bars, reduces structural variability, something which is again less known. And most importantly is basically expressing the timber materiality. So when the bars are encased in timber, you see a timber structural component rather than, a combination of timber with other materials. Among the steel bars or rods available on the market and we could get our hands on, there are quite a wide range, but we have picked up a few. We looked at application of normal ductility reinforcing bars, fairly cheap, abundantly available, and they, let's say, characteristic yield strength is around 500 MPa. Also, we looked at application of threaded bars, 4.6, 8.8, and 10.9. 10.9 is very high grade. Doesn't have much application to my knowledge in construction industry, but 4.6 and 8.8 already used in construction sector and building industry, especially in the steel structures. The main issue with use of threaded bars, I would say it's the limited length. We could get only our hands on 3-meter long pieces, which is, of course, a limitation. If you want to build longer bars, the solution would be, of course, using either N-class bars or basically go with the mechanical couplers. So we can splice them mechanically and increase the lengths to whatever is desirable for our structural components. Now, essentially, what we are going to look at today is a frame. And I just want to make it clear, it's a moment-resisting frame, and I will explain why really it's important to look at these moment-resisting frames, not other type of frames, let's say. So this is alternative one, showing a schematic of a moment-resisting frames, different components. There are columns, beams, and the connection joint zone. I have tried to separate them for obvious reasons, which I would try to explain further down the track. That's alternative number 2. That's another way we can build like some moment-resisting frames or frames with moment-resisting connections. So you see in this case, the connections are at points of contraflexure where the bending moments are relatively small. That's another alternative. Of course, if the columns are interrupted at these locations, we have loading perpendicular to the grain in the beams, and that would have some implications from, let's say, short-term and long-term performance point of view. Now, I take alternative number 1 and show you what it looks like when we put reinforcement in this frame. So that's what we are going to look at, connections. As you see, the intersection between beam and columns, beams, and then we put reinforcement in the columns. So that's, of course, the cross sections we are looking at. And these reinforcement, as you can see, they have been curtailed in the joint zone. And again, they provide means for connections similar to, let's say, glued-in rods. Likewise, in the beams, we have reinforcement, which are running continuously throughout the beams, and they are curtailed at the location of the nodes, joints. And then these reinforcing bars in the beam can provide means for connections. There are certain advantages comes with this kind of moment-resisting connections. I just list them here briefly, and I provide one example towards the end of this presentation. Of course, these moment-resisting connections would allow less deflection in the beams. And then, apart from that, they can be relied on as part of a lateral load-resisting system. So less deflection means that smaller cross-section and less material, of course. And in terms of lateral load resisting system, if we have moment resisting connections, we can completely eliminate the bracings, or at least reduce the number and size of those bracings in the structure. So that's the main goal of this research project. So to have or develop a moment resisting frames that can be relied on as part of the lateral load resisting system, of course, would allow reduction in the cross-section sizes. Now, let me show you one slide at least on the fabrication and what sort of process we use for fabricating these structural components. You see on the right, this is our CNC machines. We were lucky to basically get this one last year, and it helps us a lot with basically processing these pieces of timber. And we can now, let's say, fabricate beams, columns up to 6 meters in length without any issue in our laboratory. So the process starts with planing of the timber. If they have prime coatings, we have to remove that because of obvious reason of the bonding, to avoid any issues with the bonding of these pieces. And then we cut these grooves, as you can see, half grooves. And then the next step, we just apply the adhesive, insert the rods and apply the adhesive, and then laminate these pieces. And that's what the final product looks like. I would like to draw your attention to this end. As you can see, there is the hole size at this end, the groove size is slightly bigger, and that's for the application of the couplers. So we have enough room to use the couplers, and you can see the couplers at these ends. So at the end, the final products can be assembled easily by bolts and nuts. And that's the reason we are going through this process. The type of adhesive we have used is polyurethane adhesive. It's Loctite. It's a 2-part adhesive, and Loctite 810. And we have learned quite a lot over the past few years by using it as adhesive in our fabrication process. One of the challenges in fabrication of these glued or block glued laminated timber pieces or reinforced timber pieces is basically applying the pressure during the curing process. Initially, we used manual clamps, something you can buy off the shelf, let's say from Bunnings. But later we noticed it's really important to apply sufficient pressure during the curing process, and it becomes quite critical, especially for larger structural components like these ones. So we built this, let's say, fabrication platform, and we use now mechanical clamps. We can clearly control the amount of pressure applied on the beams or columns we fabricate by tightening these and using some torque meter wrench to measure the amount of post-tensioning applied on these mechanical clamps. So now, as I said, we can build beams up to 6 meters long easily with this system in place. Now, with that introduction, let's just have a quick look through the experimental program, and then I will go through the design provisions. The experimental program consisted of two parts. We had short-term testing, and then we had long-term testing. In the short-term testing, we look at the axial loading capacity of the columns, four-point bending of the beams, reinforcing bar pull-out was also important, done embedment test, static and cyclic bending test on the connections to demonstrate the satisfactory performance in terms of stiffness, strength, and ductility, the three factors which initially I highlighted. Also, we'll look at the long-term performance of the columns, meaning that we applied loads on the columns and we monitored them for over a year, and some beams which are at least at the moment under the loads, and we are planning to monitor them for 18 months to 24 months. And I show you again some primary results of those long-term bending tests. And also we have long-term reinforcing bar pull-out, right? Because we want to see whether this bond between steel bars and timber would be affected over time because of the creep of timber and mechanosorption effects and the other long-term effects. Now let's look at the short-term bending test on the beams. So as I said, we have beams, columns, and connections. I take you through each one of these components one by one, and then at the end, try to just assemble them back so you will see in a system how they perform. So this is an example of a beam subjected to four-point load. The cross-section is 190 by 135, consists of 3 lamellas of pine in this case, MGP10. And then we have some fair also laminated in this case. I believe in total we have tested over 100 beams and over 120 beams and columns, different size and span lengths ranging from, let's say, 1.1 meter in height in the columns up to 6 meter long for the beams. And that's what the failure mode look like when we have reinforcement. You see crushing or development of a kink band in timber, and tensile flexural failure in the tensile zone of the beam. In this case, basically it's initiated from the location of the nuts. The main goal was to establish the bending moment capacity, bending stiffness, failure modes, and ductility when we have this reinforcement in the system. Again, another example of a four-point bending. In this case, we have laminated GL8. And we have 3 lamellas. Each one is 65 millimeter. The depth is 280. The span is 4.8. And you will see this is the failure modes. So to just summarize, the intention was to test a wide range of timber species, grades, with different amount of reinforcements and different reinforcing ratio and locations in terms of having bars only at the bottom, top, or top and bottom, to see whether there would be any difference in terms of performance and what would be the optimum reinforcing ratio. Now let me show you this load versus displacement diagram. On the vertical axis, you can see the load. On the horizontal axis, you can see the displacements. So these are the 2 reinforced alternative beams we have tested, one with only reinforcement at the tensile zone, the other one in the compressive and tensile zone. And then, of course, the unreinforced alternative, the load displacement of the unreinforced one is the red one. The peak load is around 45 kilonewton with only reinforcing bars in the tensile zones. This alternative on the left, you see this green curve. The peak load comes up close to 65 to 70 kilonewton. And then when we have reinforcing bars in both compressive and tensile zone, the alternative on the right, which is a 190 millimeter deep beam, the peak load goes close to 115 kilonewton, which is a substantial improvement in strength. Now, if you want to see what the percentage of improvement in peak load and stiffness, we saw 25% and 41% in peak load and stiffness in the case of singly reinforced, you see on the left, and in the case of doubly reinforced, 69% and 120% improvement in peak load and stiffness. Now let's look at the other beam, which is a GL8, and this GL8 was tested in with two types of reinforcement. I just showed you the results of reinforced beam with N-class bars. So the yield strength is 500, and it's normal ductility reinforcing bars. So this is the beam you see on the right, 200 millimeter deep, and it consisted of 3 lamellas, 195 millimeter wide. These are the location of the bar. We use 4 and 24 bars. And you see the red one is the load displacement of the unreinforced beam, and the blue one is the reinforced beam. One thing I would like to draw your attention to is the difference between the peak load of these two versus the peak load of these two. You see, when we have reinforcement in the cross sections, the variability in the peak loads reduce quite a lot, and also in the stiffness. You see, interesting in this particular case, it seems it's even the same test, but in fact we did 2 tests and with minimal variability in the results, right? And the slope of these lines, again, I would like to draw to your attention to, it's the stiffness or a measure of a stiffness. Now, in this case, up to 89% improvement in the peak load or strength and 72% improvement in the stiffness. Now, let me just explain it in simple terms what that improvement means if you want to see what's the performance of this new reinforced cross-section like, and it's on par with what GL grade. Keep those two numbers just in mind, 89% and 72%. Now, I took this table, which is table 7.1 in AS 1720, and look at this table. The beam initially we picked up was GL8. The bending strength, of course, the characteristic value is 19, and elastic modulus is 8,000, all right? Now, let's multiply this bending strength by 1.89, which is 89% improvement in peak load. Now, the bending strength is equivalent to 35.9 or 36 MPa, roughly. And in terms of stiffness, which is similar to, let's say, elastic modulus, if you want to convert them, 1.72, that 72% improvement led to this elastic modulus of 13,800 MPa. Now, if you look at this table, you will see it's equivalent or even above GL13. So you'll see by adding 4 and 24 bars, we converted GL8 to GL13. In fact, this bending strength is closer to, I would say, GL15. Some of the glue lamp or beam 15 I have seen on the market, they have bending strength of 36 MPa, which is very close to that one. And the elastic modulus is even slightly higher than GL13, but let's say it's GL13 for now. So you see the substantial improvement in the strength as well as stiffness. Now, let's look at the long-term test result. This is the test we did to establish, one, the long-term deflection over time to see if we add additional load on these reinforced beams, would that lead to excessive deflection? Would we have any problem with excessive creep, etc. over time? And we have, at the moment, 16 beams, which have been monitored over the past 2 months. And we plan to run it, as I said, for hopefully 18 to 24 months. This is where the loads are applied, and then the load cells and a wide range of instrumentation. You can see these cables. We have, I believe, over 120 channels to monitor different things. In addition to that, we have some mechanical gauges to measure the slip between the bars and, you know, change in, let's say, slip and the bond between steel and timber over time. And we have both Douglas fir and radial propine monitored. Now, this is the midspan deflection versus loading. This is something I prepared around 2 weeks ago. So it was around 6 weeks into the loading. So the range of the loading, you see the loads for unreinforced one, the dot line is 13 kilonewton. When we add reinforcement to that one, 20% of that was 19.5 kilonewton, which is 50% higher than, nearly 50% higher than this 13 kilonewton. All right, then that's the improvement. So we applied higher load on the reinforced alternative. But if you compare this one, the dashed line or the dot line, with the solid line, you clearly see the unreinforced alternative subjected to even higher loads has less deflection, around 17 millimeter versus 19 millimeter, 20 millimeter for the unreinforced one. We applied again higher level of the loads on similar beams, and that we came up to 30%. And you see now for unreinforced beam, it's 19.5. For the reinforced alternative, it goes to 29 kilonewton. But let's compare this again, dashed line with the solid line. You see the peak displacement or the maximum displacement after like 6-7 weeks is around 23 millimeter if you took the average, and it's more or less the same for the unreinforced and reinforced one, with the big difference being in the reinforced case, we have 50% higher load applied. So it means that really steel is doing its job and taking the load and the stresses in the process. Then we did the short-term test on the column. So apart from the beams, which I showed you the bending test, let me just show you quickly some of the test results and failure modes on the beam. Again, the main goal was to look at different grade of timber, different amount of reinforcement, different grade of reinforcing bars in terms of yielded strengths, and look at the slenderness as an important factor in design of the columns. And so far, we have tested columns up to 2.7 meter in length, and we are planning to do additional tests on columns up to 3.6 meter long in the next few months. So a range of failure modes you see is starting from crushing, development of kink bands, to, let's say, splitting or buckling and secondary bending of the beams. These are sample load versus displacement. So as I said, we tested a wide range of column with different lengths. Even we went down to 300 millimeter long, and we went up to 2.7 meter in height. And I have showed you some sample test results. Just two key findings in terms of the performance were: one, there is an optimum reinforcement ratio for the columns, and it's in the range of 3.5, and I would say it's closer to 4%. So, and substantial improvement in terms of the load carrying capacity, nearly over doubled the load carrying capacity in the low grade softwoods when we use close to 3.5 to 4% reinforcement in those. We did long-term tests also on the columns to see what's the long-term performance. It's indoor controlled environment and indoor uncontrolled environment. This is the uncontrolled one, and this is the controlled one. It means that we kept the relative humidity and temperature in the room constant for nearly 16, 17 months to see what's really happening. And then we put the same columns in the lab environment. So we couldn't control relative humidity and temperature in this case, and we compare the results to basically separate the creep effect from the mechanosorption effect and the variation in the relative humidity and temperature. We also did full-scale test on two columns. You see these are 2.4, and they were subjected to indoor uncontrolled environments. This type of graph is what we get from those long-term tests on the columns. So you could clearly see the creep behavior and the deformation, which is increasing over time. And we could get, an additional like 25 to 35% increase in the shortening of the columns over time, over like 14 to 16 months, at the level of loading 30 to 35% of the peak load, which is, I would say, a very high level of the load on the service condition. Now, so I covered short-term, long-term test results. So before I dive into the design provisions and what we did to demonstrate application of these reinforced timber beams and columns, I want to just show you this slide because it has really major impact on the way we treat these reinforced timber beams and columns. So we really need to determine what's the bond between these steel bars and timber. As I said, we did some bar pull-out tests, so to determine what's the quality of the bond like and whether we can yield the bars, and pretty much I would say with no exception, we always could yield N-class bars. Not really 8 bars, but N-class bars could be yield. And just bear in mind the yield strengths of those bars, the mean value is close to 580 to 600 MPa. And to basically establish the bond and see what's the bond behavior, we just use the DIC on many specimens, columns, and beams, and also we install the strain gauges on the steel bars and compare the strain in timber with strain in steel bars to see whether there is any difference or the difference is small, and hence we can assume there is a perfect or near perfect bond between steel and timber. And this is one sample graph. You could clearly see timber strain from DIC is the blue one, and the steel strain from strain gauge is the dark solid black line. And you see very close correlation that clearly indicates there is near perfect bond between steel and timber, and that would basically pave the way for adoption of some simplifying assumption in the process of design provisions and development of design provisions. Now, I just take you through some of the design provisions we have in 1720 as well as Eurocode, and then see how we can use those or modify them to essentially, let's say, compare them with or use them for this reinforced timber. On the left, you can see design provision in 1720. On the right, design provision from EC5 or EN 1995-11. And one important factor in these formulas is basically these parameters, K12 in Australian standard and KC, which is like a buckling factor in Eurocode. We really need to establish these parameters for reinforced timber and come up with, let's say, some design provision in design of the columns. And please look at the range of the slenderness value we have in Australian standard. So for row CS, less than 10, we consider the columns stocky. There is not much slenderness effect to be taken into account, but then we have intermediate slender range, and then we have slender range of the columns in here. So, and you will see we really need to change this because when we add reinforcement, it has some impact on the way these columns behave. Now, what's the slenderness factor? As I said, K12 or KC, it's nothing more than basically the peak load of a slender column divided by the peak load of a stocky column. Now look at this graph on the left. From 1720, you see a range of test results basically placed here on that diagram. And then you can see the black solid line, which is the AS 1720, let's say K12 formula. And then we have reinforced, unreinforced timber test results. And you can clearly see here in that range, the test results are below the curve. It means that K12 value coming from 1720 in its current form is not really very conservative too. So now what we have to do, we have to propose new ranges for the stocky, intermediate slenderness and slender columns in this case, and that's the way we have come up with these ranges according to this, let's say, calibration. And then for Eurocode, we did the same exercise, and we modified the Eurocode formula, came up with something like this, which looks like very much similar to what we have in Eurocode, and we only add a power to that and change this, let's say, curvature parameter as well as the reference slenderness values. Now, with that, let's look at some design examples to see how reinforced timber columns are stacked up against, let's say, bare timber columns. So this is one example. It's an office in Sydney. It has like 7 levels. And then you can see the layout. The span is 9.5 by 9, and we took just one of the middle columns. And you can see the loadings on the right-hand side and some of the assumptions. So this column in the original design, which was a bare timber column GL24H, with this mean elastic modulus, characteristic elastic modulus, compressive strength, and height, 3.7 meter. The cross-section size was 540 by 540. The axial force without any live load reduction factor was close to 4.8 meganewton. And then after considering the live load reduction factor, it came down to 3.8. Now, when we look at it based on 1720 and EC5, these are the load carrying capacity we got. We got 4.8 meganewton from 1720, and we got 4.4 meganewton from EN 1995, all right, which are not really that far from this range with and without live load reduction factor 3.8 to 4.8. Okay, and these are just the bare timber column. Keep that in mind, 540 by 540. Now let's move on to the column and design the alternative with reinforcement. That's what happened if we use GL24H and reinforce it. We could reduce the cross section from 540 to 540 to 425 by 495 by adding, let's say, these 10 reinforcing bars and 32 into the cross section. Okay, now, and that's the details of the calculation you see on the left. On the right, let's just go for a lower grade, because that's the purpose of our project. We want to use low-grade timber and utilize it in such a way that can be used for a very demanding situation. Now, in this case, we have to use quite a fair bit of reinforcement, but again, they come in the lamellas and they can be, fabricated. There is no problem, and there is like enough cover for them for, getting some fire rating according to deemed to comply, let's say, or sacrificial layer. And this is the alternative GL8, which is not really that far in terms of size to what you see. Now, let's look at another example. This is another office in Canberra. So this one was designed using some high-grade glue lamp. The original size was 380 by 380. Now we redesign it with GL17 with reinforcement. We could reduce the size to 330 by 340. That's one. Let's say we don't want to use high-grade glue lamp. We want to go with GL8. If you go with GL8, the size is slightly increased, around 40 millimeter or so, with some reinforcement, but we could get a capacity similar to what we saw from high-grade, let's say, glue lamp columns. Now look at another example, a timber beam. So on the right, you could see the dimension, 480, 840 millimeter deep. These are the mechanical properties. This is again GL24H according to EN 14080. And then the characteristic bending strengths, the span length is 9.5. And then we did the calculations based on a simply supported kind of beam. And that's the ultimate bending moment we got. Now, if you look at the design according to 1720 and we apply all those K1, K4, K6 temperature, let's say partial seasoning and all those factors in the design, we get like 921 versus 870 from Eurocode, which are again meeting these requirements. But now let's look at the reinforced timber alternative to see what the sizes are like. So on the left, this is the original size, 840 by 480. This would be the size if we reinforce it with 4 and 30 and keep the grade the same, GL24H, and then leave like 85 millimeter cover. And that's the range of cover. Again, I want to emphasize we considered around 85 millimeter or so for most of our design to, let's say, meet a minimum fire rating requirement of 60 to 90 minutes, assuming that charring rate is 0.6 millimeter per minute or so. And this is the detail of calcs. Again, on the right, let's use GL8, the original size. If we use GL8, again, the size could be reduced quite substantially, 720 by 425, with the same amount of reinforcement. Bending moment capacity is 894. So you could see there is quite a lot of benefit in using this. Now, let's look at the connections and see what those connections are. First, I just show you some concepts. I have to also acknowledge contributions from Nick Houston. I believe Nick might be here today. During a period, we had the pleasure of working with him very closely on this project. And to develop some of these concepts, Nick had really contributed a lot and helped us a lot to better understand the constructability of these connections and ease of fabrication, etc., and what's really expected in a construction site. Now, I would like to basically classify the connections to two types, permanent and the constructible one. When I say permanent, it means they can't be easily dismantled at the end of design life or at any point in life. So it requires like, demolition of those connections that would cause damage to the structural components like in beams and columns. These type of permanent connections mostly involve cementitious material or use of cementitious material, whether as steel fiber reinforced concrete or ultra high performance concrete with steel fibers. That's something we are exploring at the moment. Or the constructible, again, in our case, we use steel joints with bolts and nuts that nicely go with those couplers, which I earlier showed you, and clearly they can easily assemble, similar to the way we assemble, let's say, steel structures. Some of the concepts, we look at it, you see columns entering a joint zone or a frame zone. In this case, we have a tube as a backbone of the joint zone. In this case, we have a rectangular hollow sections. You could see some plates, like slotted in plates. They can be used as slotted in plates, provide additional, let's say, stiffness and strength to the support. And these are other alternative, a range of, connections we looked at. And again, in these ones, you could clearly see they are slotted in plates, which can be used for connection in the second directions. But again, the purpose was to basically utilize those reinforcements. So how that works, we have holes you see on this face of the flanges, and they sit in front of the holes coming from the couplers at the end of the beams, and we can bolt them to the back of these plates. Likewise, here there are holes, and we can assemble them very easily. So this is one of the earlier examples you see on the right top, and that's what we are looking at to build a frame and test it at the moment. So we tested quite a number of connections. This is one of the connections. I want to emphasize these connections have very, very stiff joints, but they are deconstructible, and we can test them several times. That's another nice feature about these, meaning that you have high level of seismicity in a region, and there are damage. Those damage only limited to these end zones and not really structural timber elements. So what we call is a concept of a fuse coming from seismic design of structures, and those fuses can be easily replaced. This is one example. This has been tested like this. We apply a push or a pull, and we can look at the bending moment capacity and performance. And we did, of course, quite a lot of advanced finite element simulations to look at the behavior of these joints and do parametric study to utilize them. This is the bending moment versus rotation of that connection I showed you in the previous slide. This is the cross-section size, which is not really a large cross-section size, right? And then this is the stiffness, slope of that line. The stiffness, if you calculate it from that slope, is 3,272 kilonewton meter per radian. And just bear in mind, it's for a near rigid joint. So we would have additional deformation, which reduce the stiffness if we, use, let's say, for example, that deconstructible joint. But that's something you could get it from the existing models available in the literature, and they are widely adopted in European standards. Now, let's see if we implement that joint in a frame and make it a moment-resisting frame, how that would impact, let's say, the deflection, which could become quite a governing factor, or it's pretty much the Achilles heel of long-span timber frames and timber floors. So this is the example I put together, a 5-meter span, let's say, frame, 2-story, 3.3 meters in height, and we have a short-term service load of 12 kilonewton per meter, calculated according to AS 1170. Right? The connections, just bear in mind, these connections are simple connections. These are pinned, right? So we have rotation at those joints. Now, we have the same frame, but now in this frame, we have implemented those joints, which have some additional stiffness, that stiffness which I showed you here, coming from this kind of diagram and test. Now, look at the deflection. I took an interior span, delta 1, deflection. For this one, it would be delta 2. And of course, due to the fixity provided by the connections, we don't have like free rotation here. The rotation is restrained. And then deflection in this case is 17.9 millimeter. And in that case, it's 10 millimeter. You see, there is a huge difference between the deflection of these two. We are using the same beam and column size. It's just the connection that makes such a huge difference. Let's say even if this stiffness reduced by a factor of 2, or it's halved, right? Because we have joint deformation in the joint itself. Still, this deflection can go up to close to 12.5 millimeter, which is way less than 17.9 millimeter. And that clearly highlights the advantage of using these connections or moment resisting connection, let's say, in the frames under service condition. And of course, on top of that, we have, these moment resisting connections working as part of the lateral load resisting system. All right, to just wrap up my presentation, I'll just show you this one, which is what's next or what's happening at the moment and we are working on. And part of it has been done. And the other part is an ongoing part of the project. And hopefully we will be able to, come up with some results very soon. The first thing is basically calibration of this capacity reduction factor phi, which we needed for design of beams, columns, and connections in the context of, let's say, building code we have, and probability of the failure, whatever that is, or a reliability index according to building code of Australia. So we have this beta, which is like 3.8, 4.2, which represent probability of failure, and we are calibrating this phi for reinforced timber. Right, and necessarily the phi value we have for timber is not going to be similar to the phi value we have to apply for the reinforced timber one. We are testing at the moment some connections with ultra high performance concrete, and the deconstructible connections, we are doing also some cyclic tests on them to demonstrate what's the ductility like, what's the energy dissipation capacity like, and from there we need this Q factor, which is used for base shear calculations. When we implement this connection in a frame, we need to calculate base shear, let's say, according to EAS 1170. And as part of the process, you would need this Q, let's say, which comes in different names in different standards. And then we plan to build, which is, again, that's something happening at the moment. Hopefully in the next months or so, we have these frames built and tested. We are planning to build 2 portal frames, again, full scale or near full scale, 2.7 meter in height and over 5 meter in span, to test them, so we can see the performance of these beams, columns, and connections in a frame firsthand, and from there, get the proof of the concept for a real frame. And the last bit is basically developing a phi value for the whole system for a frame rather than beams and columns, which is going well beyond the standard we have at the moment in Australia and around the world, which are typically reliant on the capacity reduction factor for beams, columns, and connections, or elements or member, rather than the whole system. And hopefully we can achieve further improvement by pushing on that front. Okay, and with that slide, I come to the end of my presentation. Hopefully I didn't go over time, and thank you so much.
Thank you for being here, and thank you for that incredible presentation. You know that you're onto something when you improve more than one thing at a time, and it's fantastic that this approach is so clearly improving the performance, not just the elements themselves, but also lending directly to a very simple, direct, and strong connection regime as well. Like you can imagine a very clear path for designers to be implementing this and making significant savings and rationalization of the design as well. You can imagine that for some buildings you could eliminate costly brace bays entirely, and in others you could massively rationalize the column and beam selection in extreme places while keeping it uniform throughout the rest of the structure. This is a great time for Q&A. If anyone in the audience has any questions, please shoot. We'll have a brief discussion about this before we close. So yeah, thank you so much for being here. I've got some questions, which I'll start with.
Sure.
In the with the fabrication technique, in systems that have glued components, we often face questions in regards to quality assurance and checking and non-destructive testing of gluing. Is that something that your team has considered?
Look, the way we look at it since the start of this project is I don't think the process of fabrication would be significantly or grossly different than what we see in the fabrication of the glue lamps. As you see, there are additional steps, interim steps, let's say, that should be taken, additional processes, which I believe would not really affect the way, in fact, we build this thing, and they would not be that different from the glued laminated fabrication process, right? It's just a matter of inserting steel bars and applying or extrusion of the adhesive layers, and then applying that pressure, sufficient pressure, curing time, and that should work quite well. As I said, we have tested many specimens, and as you can imagine, the facility we have in our lab, they are primitive, I would say, compared to what you will see in a real manufacturing, like, let's say, facility, right? Or a fabrication facility. But still, I told you, and unfortunately, I didn't have enough time to show you. We have tested like 8 bars, which has the yield strength of close to 700, over 700. And we have glued this in timber, MGP10 and F5, F7, and they are like 45 millimeter thick. And we just tried to pull them out over 1 meter length. And pretty much we always manage to yield these bars. Even 8 bars, a lot of time we managed to yield them, right? And as I said, look, as you could imagine, even though we really exercise due diligence in the process of fabrication to make sure that it's on par with what you will see in a real life, still I would say, a lot of work's done by PhD students, and it takes them time to learn and apply and trial and error. But as I said, we have managed to really accumulate a wealth of knowledge on that front. And now we are fairly confident based on the test results we have. And I'm not talking about 1 or 2 tests. I believe we have done around 24 embedded, bar pull-out tests, and pretty much all of them came up quite consistently with not huge variation in the test results. So you will see they take loads close to 300 kilonewton, let's say, when we have N24 bars embedded in timber, and we try to pull it out, which is well above the yield, I would say.
Were you finding that they would yield at the exit point of the timber?
Exactly.
Yeah.
Exactly. That daily yield at the exit points, because, well, as soon as the timber steel enter the timber, you will see a composite cross section, and you can clearly see very nicely we have necking of the steel bars outside, just outside the timber.
Wow, that's fantastic.
Yeah.
Fantastic. Have you considered applying this into purely to attack vibration of, say, a CLT floor?
Very good idea. Honestly, I've been tempted to do the same thing, to have some laminated CLT floors, and we have the facility that CNC would allow us. Honestly, we don't have the room. As you could have seen in those pictures, our lab is completely cluttered and full with quite a lot of long-term specimens. And apart from these, at the moment, we are running some long-term tests on like 8-meter span CLT concrete composite floors at the moment, along with vibration tests. And they have also taken quite a fair bit of our laboratory. If you come and visit it, you would notice. Definitely, as soon as we come to the end of those projects, I would love to give this a try. Especially, I feel that could provide a nice solution for long span CLT flat plates or flat floors. Let's say we have 360 millimeter or 90 millimeter thick CLT panels laminated with some steel bars, and even those could be necessarily not bonded. They could be just, like strands, and they could be post tension, let's say, just as an alternative. But yeah,
oh, you could also just flat plate it underside in a thin sheet. It wouldn't need to be a bar if it's just for serviceability, potentially.
That's correct. Yeah, but again, if you want to look at this, we really need to go like 8-9 meter span. As I said, the space is at the moment quite the bottleneck in our laboratory, right? But yeah, no, very good idea, and definitely I will give it a shot. Hopefully in the next year or so, as soon as we come to the end of this
Well, it all
project.
seems like quite a rich place to be searching for solutions. I've got 2 more questions here. From Jesse and Nick Houston. First one: what is the time frame for publication of design guidance? And is anyone looking at commercializing this? So
Look,
big question.
the major obstacle, I would say, Kylan and Nick, hello. Look, it's the phi value we are working on at the moment. Again, unfortunately, I was short of time because At the moment, I have two PhD students specifically working on the phi value, what sort of phi value we have. We have got to a very good place because the way it works at the moment, we build a numerical model, we calibrate it against those test data, and then we used those numerical models to generate millions and millions of data points. And we use that to basically draw the line and say, okay, this is the line. Below this line is, let's say, the unsafe zone with reliability index below 3.8, 4.2, and above that is the safe zone with the beta bigger than 3.8 or 4.2, and that's the phi corresponding to that beta value. And that's where we are at the moment. Look, I'm trying my best, let's say, to hopefully come up with at least a preliminary design guide by mid next year. And I'm hoping that we could get there by then. Not the reliability of the system. You see the last item in this slide, because this is quite, I would say, beyond the level of the work you have seen so far in the standards and even in academia. And it's at very infancy, I would say. But the phi value for beams, columns, and connections, I'm fairly confident, hopefully by mid next year, we would get to some place that we could have some preliminary design guide.
Fantastic. Sure, a lot of people would eagerly await that. Question about service class and using these, I presume, in external environments as well as internal environments. Do you think that it could be suitable for use, say, outside, and how moisture content and changes in the moisture over time might impact long-term performance?
Yeah, that's a very good question. I believe the same type of challenges that timber, when it's exposed to external environment, we would see it with reinforced timber. I wouldn't expect completely different things. So environment, change of relative humidity and temperature, they are the same beast, no matter whether we have reinforcement or no reinforcement in the timber cross sections, right? But in terms of the expansion and contraction, there might be some issues around the use of reinforcement. Honestly, I don't have let's say, exact answer to that question. Again, that's one of those things we initially planned to do, but then I changed my mind. Obvious reason, I thought, okay, it's going to be a service class 1 or 2. Why we should bother to really expose it to harsh environment, like, with significant change in relative humidity, direct exposure to, let's say, humidity, etc. But one thing I can say, if you look at some of the test results I show you, we use GL8 at the moment. And those GL8, all of them, which is quite a pain in the neck, I would say, come with some primer coatings. And to my understanding, at least we couldn't find anything without any primer coating. And they do that to just provide some level of protection, at least during the construction phase, which timber and timber structural components are the most vulnerable during that period when subjected to rain and moisture, right? So we can do the same thing with this kind of reinforced timber when they are done. So even you see the exterior surface is completely covered in primer coatings, right? And that would provide a level of protection or a layer of defense, at least to some extent, if not completely.
Like a prime area for, again, yeah, more investigation. Last question here today, I think, before we wrap up, is what is the most promising detail you tested that is the stiffest, that generates the most stiffness in the connection itself?
We haven't tested it yet, but from some earlier analysis, we know that the connection with ultra high performance concrete, I can tell you, would be definitely stiffer than the constructible joints. But look, it's all about making some compromises. The constructible joints has the advantage of easy assembly and easy dismantling of that. At the end of design life, reusing, recycling, repurposing would be extremely easy, versus those permanent connections, as you could see with ultra high performance concrete, they are there forever, right? And there would be advantages with those. For example, there is inherent fire resistance in those ultra high performance concrete joints. We wouldn't be too worried about exposure to fire and vulnerability of the whole frame or connections to elevated temperature. But yeah, they become permanent connection, as I said. But ultra high performance concrete definitely would be the way we're gonna test it. And we are hopefully test the first series of our specimen, which are 8, by sometimes mid-September, and by then I will have the test result. But I'm fairly confident those are the stiffest one.
It'll be very curious to see how you construct that in a clean way to try and keep the concrete tidy within that compressed zone.
It's nothing special. I had a detail on that one. It's like a box sitting on the top of the columns, and the nuts are tight, and then the beams enter that box, rectangular hollow sections. The nuts and bolts are tightened inside the box, and you just pour that box with ultra high performance concrete.
Right.
Fairly easy, straightforward. And after a day, we did some preliminary tests to make sure the quality of this ultra high performance concrete meets the expectations. We could get a strength of up to 55 MPa after 24 hours,
Wow.
right? Tensile strength of 3-4 MPa, which is enough for adding the next level on top of that.
Certainly.
And that was essentially the reason we decided to go down that path, because we want to be very quick. We don't want to wait again another week or so for the concrete to cure, and then we could go for the next level. We wanted to do it just bang, 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 one after another very quickly. And after 48 hours, it gets to 72, 73 MPa, right? So it gives you the window for, assembling and putting
the story above that. Again, you could easily imagine a 5 or 6 story building being made out of GL8 timber being constructed very quickly with no brace bays at all. That would be an incredible opportunity for our whole industry. Well, fantastic. Thank you so much for being here. Thank you for answering the questions and for sharing your team's research with us today.
Absolutely a pleasure to be here. Thank you so much, Colin, and thanks everyone.
I'll do a quick outro before we go. So the next installment of this WoodSolutions webinar series will be on the 3rd of September, and it will be New Innovations in Timber Products and Systems, State of the Nation. So Alistair Woodard will talk us through the latest in timber products coming out of Ash and Timberlink through Chris and Jeremy. So don't miss that one. And of course, don't forget that the Australian Timber Design Awards for this year have now closed for this year. So get ready for the People's Choice Award, which will be opening soon, right after the Timber Construct conference, which is occurring next week in Melbourne. So if you have not got your tickets, check it out. It's going to be a great conference, and we'll see you there. So thank you very much, and we'll see you at the next webinar. Cheers. Bye.